Hi folks, we're going to take a look at number 24 on page 158. So let's take a look at the question. It says a boat leaves a dock 2 p.m., heads west at 15 kilometers an hour, and then another boat heads south and reaches the same dock at 3 p.m. And they want to determine when the boats are closest to each other. Okay, so we have one boat moving west and another one that's moving towards the dock, so it must be coming from the north to the south. So I'll draw my dock a little further down and to the right, so I have enough room to draw a nice diagram. So here I have my first boat that travels in the west direction for a certain amount of time. Okay, and then the other one starts somewhere north of the dock and moves southwards towards the dock. Okay, and what we want to know is when are they closest to each other. So in other words, we have to minimize the distance between them, which would be the straight line distance between them. All right, so this hopefully does look familiar, and you see in this diagram hidden, or maybe not so hidden, is a right angle triangle. Okay, and we are looking for this distance here, which I'll call capital D, so I don't mix it up with the D in a derivative. All right, so we need to find a model for this distance between the two boats. Well, assuming that they're traveling at a constant speed, we remember that we've got our speed equals distance over time equation. So given that I know the speeds, I can actually come up with an expression for their distances with respect to time, because d is just equal to vt. So for this one here, it has traveled in this unknown amount of time 15 t kilometers. Okay. Now this is where you have to be careful, because what I'm looking for is this third side of the triangle, but this does not represent the distance that the first boat has traveled. This would represent here 12t, the distance that it's traveled, okay? But that's not the length that I'm looking for. But they do give us this other piece of information. It says that the second boat reaches the dock at 3 p.m., meaning it's only traveling for 1 hour. Okay, and since it's traveling at 12 kilometers an hour, we know that the total distance is going to be 12 kilometers. So that means that this little portion here is just 12 minus 12t. Okay, and so now we're ready to come up with a model. So just going to use Pythagoras here. So I've got d squared is equal to 15t squared plus 12 minus 12t squared. Okay. And I do have the option to work with this using implicit differentiation. I don't have to isolate d and work with the square root. So now that we have that tool, we certainly could solve the problem implicitly. Okay, but what I'll do is I'll use our more traditional calculus methods, and since I'm able to isolate d, I'll do that for this particular circumstance. Okay, so let's simplify a bit. The 15t squared, 15 squared is just 225, okay, times t squared. Now this one here I'm not going to actually multiply out because it takes some time. It's going to give me a bunch of terms, because I know that when I have to differentiate this portion, I can just use the chain rule. Okay, so sometimes you use the chain rule not because it's a necessity, but it just makes life a little easier. Okay, saves me from having to do that. Okay, so what we have now is a model for the distance between the two boats with respect to one variable. All right. But before I go, I do want to see what the restrictions on t is. So if I assume that t starts at 2 p.m. when this whole experiment begins, so I'll let t be the time from 2 p.m. Well, once this second boat reaches the dock, this other one keeps going. Their distance is only going to get bigger from each other, from the other. Okay, so it's very clear that at 3 p.m. any time after that is certainly not going to represent when they're closest to each other. So what we can do is just restrict t to be between 0 and 1. Okay, so essentially from 2 p.m. to 3 p.m. So since it's a closed interval, I know I'm going to be able to determine the absolute minimum by just testing the endpoints and any critical points that lie in that interval. All right, so let's take the derivative here. So I'm going to skip a few steps here. I won't write as much as I normally do because we've done this type of thing lots of times. So I know this is this whole function inside to the 1/2, so it's going to be 1/2 times this function to the negative 1/2. So it's just going to bring it into the denominator. as a square root. So square root of 225 t squared plus 12 minus 12t all squared, okay, times the derivative of this inside function. So let me take that here. So this is nice and easy. Just t squared is 2t. So this is going to be 450t. And here, this is what I was talking about before. Instead of multiplying this out, I'm just going to use a chain rule on this thing here. So plus, well, this is like u squared, so 2u, 2 times 12 minus 12t, times the derivative of 12 minus 12t, which is just negative 12. Okay, and I have something nice and simple to expand. All right, so remember, we're looking for the critical point, so we'll make d prime equal to 0. So all this in the denominator, I'm actually not going to be interested in because, of course, in order to determine when a fraction is 0, I just need to look at the numerator. So 225t squared plus 12 minus 12t all squared will be the last time I write that. All right. So let's simplify on top. So we've got our 450t. And then here, what do we have? 12 times 12 is 144, times 2 is 288. So that looks like minus 288. And then this is going to be the same product, but two negatives. So it's going to be plus 288t. All right. So as we said, I'm just interested in the numerator being 0. So what do we have? We've got 0 equals. So 450 plus 288. So 450, 550, 650. 7, there's going to be an extra 38 left over after the 50. So it looks like it's 738t minus 288. So t is equal to 288 over 738. And since this is an application question, I know I'm going to be going for an approximation. So let's do that here. So we've got 288 divided by 738 is 0.39. Okay. So only one critical point, and it does lie in my domain. Okay, so let's start by testing the endpoints. D at 0 is equal to, well, that is just going to be 0. So I'm just left with 12, because that's also going to be 0 squared. So square root of 12 squared is just 12 kilometers. All right, let's find D at 1. Okay, this portion here looks like it's going to be 0, because 12 minus 12. So I'm just going to have the square root of 225, which is 15. Okay, so far this is the winner. Let's check D at 0.39. All right. So here, let's put this into here and be careful. 225 times 0.39 squared. Okay, and then plus 12 minus 0.39 times 12 all squared. Okay, and then take the square root of that, so exponent 0.5, and we end up with about 9.4. Okay, so clearly the smallest of the three. So this must represent my absolute minimum on that interval. Okay, and just for the fun of it, that of course would represent the absolute maximum distance between them. So what happened at the very end. Okay, but let's see what they're looking for, and they're looking for when the boats are closest together. Okay, so it'll be, oh, sorry, I just accidentally turned on my phone, asked me a question, sorry about that. What was I saying here? Oh, when? So it's going to be 0.39 hours after 2 p.m., but that's not a particularly nice way to give an answer, so let's just calculate how many minutes that is. So what do we have? We got 0.39 times 60, which is 23.4. So my answer here, okay, at approximately, so 12:23, sorry, not 12, 2:23 p.m. because we started at 2. All right, so 23 minutes after the start of our experiment. Okay, so quick recap here. So again, get a good diagram. Trick here is to realize that this 12t is not this third side of the triangle. You have to do a little bit of work to figure out an expression for that third side. Once you get your model, whether you use implicit differentiation or you isolate and use our more traditional methods, either way is perfectly fine. Okay, and since you were working on a closed interval, it was just a matter of testing the endpoints and the critical points. All right, that's it for this one.